Now, if we know what the center is and we made a graph, so we know the shape is symmetrical, we know the center is at 1.5, we need to talk about the spread. Remember, shape, center, spread, shape, center, spread. By looking at the histogram on the previous page or 2 pages ago, we know that there was nothing unusual. There were no outliers or any points that didn't fit the overall pattern. So remember, shape, center, spread, unusual. Shape, center, spread, unusual. Shape, we saw the histogram. It was symmetrical. Center, 1.5. So the mean was 1.5. We expected to have 1.5 girls for every 3 children. We have. Now we need to figure out how are we going to do the spread. Okay. Well, there's 2 ways to talk about spread. There's the variance and the standard deviation. All that the standard deviation is the square root of the variance. So the variance is a step in finding the standard deviation. The variance is going to be very important in this unit because it is more pliable than standard deviation is. Variance will allow you to do more stuff with it than the standard deviation will. So we need to make that connection that all the standard deviation is the square root of the variance. All the variance is the square of the standard deviation. Okay, so if we go back using our example from having children with the 3 girls, how would I find the spread? How would I find the variance? First, and then I'll just take the square root of the variance to get to the standard deviation. So the variance we're going to write as sigma squared. The variance says take each individual x minus the mean times its minus the mean squared times its probability. So let's go back to the having girls. Remember that it was 0, 1, 2, 3. And the probabilities were 1/8, 3/8, 3/8, and 1/8. Okay. So the first value of x was 0 minus the mean 1.5 squared times its probability of 1/8 or 0.125 plus the next value 1 minus the mean 1.5 squared times its probability of 3/8. And I have to do this for every single value. Sucks. This is no fun whatsoever. It's too much work. So let's let the muscle do all the work for us. Let's let the guy who's strong do all the heavy lifting. So let's go back to our calculator and let's let our calculator find the variance for us. So if I go back into my favorite button, stat, edit, I want to look at these lists. I have everything I need here to do it. I just need to be smart enough to tell the calculator what to do. So again, to tell it what formula I would like it to do for me, I need to go in and make sure that I have the heading highlighted. You can never put a formula in a cell. So I'm going to make L4 equal to each individual x. Oh yeah, my x's were in list 1 minus the mean, which was 1.5, quantity squared times the probability of each one. Oh, my probability was in, whoops, I do not want that. Okay, so squared, times, where were my probabilities? Oh yeah, I put all my probabilities in list 2 times L2. Okay. Now, if you look at the formula, it says take each individual x minus the mean squared times its probability, and then I have to find the summation of that. So let's go back to the main screen. So I'm going to get out of here by quitting. Back to the main screen. Now I just needed to add it up. Well, where do I find sum? My preference is to go to catalog. And then I'm going to go to the T's and then up a couple until I find the word sum. Calculator's like, cool, I'll add some stuff up for you. What do you want me to add? I would like you to add what's in list 4. So I go sum L4, enter, and it does it all for me. So I found that the variance of the random variable for the number of girls out of 3 children is 0.75. So Now I know what my variance is. So let's take a look at that. So now I know that my variance of the random variable X, the number of girls out of 3 children, is 0.75. That does give me a value of spread. However, we're used to talking about spread in terms of standard deviation. Well, remember that standard deviation and variance are related. They're brothers. The standard deviation is just the square root of the variance. So if I want to know the standard deviation of X, all I need to do is take the square root of the variance. So now all I need to do is take the square root of my variance of 0.75. So I'm going to let the calculator do that because I don't know the square root of 0.75 in my head. So I'm going to tell it, take the square root of 0.75, which is my previous answer. So by hitting second minus sign, I can get it to bring up the previous answer. And I just hit enter. Oh, 0.866 is my standard deviation. Sweet. I didn't even need a pen or a pencil. I let the calculator do all the work for me. So now that I have the standard deviation and variance, I can talk about the spread. So my variance was 0.75. My standard deviation was 0.866. What does this mean in context of the problem? Well, on average, I expect to have 0.866 girls away from 1.5 on average. Okay. It's just giving me the spread. How spread out is the data? Now I have shape, center, spread, and as we said before, there's nothing unusual. So standard deviation is this formula right here. But really, in this process, the variance comes first because to calculate the variance, we do each individual X minus the mean squared times its probability plus the next X minus the mean squared times its probability and so on and so on. And then to get to the standard deviation, we just take the square root of the answer from the variance. So now for a discrete random variable, we know how to talk about the shape, center, and spread. Shape, make a histogram. Center, find the mean. Spread, find the variance, and then the standard deviation. Okay? And here's an example for your use later on. So we've looked at discrete random variables. Well, what about a continuous random variable? A continuous random variable can take any value in an interval on the number line. So let's say, for example, an example of a continuous random variable would be pick a number between 0 and 1. So if we think about a number line from 0 to 1, pick a number between 0 and 1. You might say 0.8. And your friend might say 0.88. And then the person next to you say 0.888 and 0.88888. We could do that forever. There's an infinite number of values that X can take. Since there's an infinite number of X's, making a probability distribution such as we did for having the children would be impossible. There's no way I could write out every single possible X value. It just can't happen. So in a continuous random variable, we're not going to be able to make a probability distribution to answer the questions. Instead, what we're going to do is go back to our old friend, the density curve. So for a continuous random variable, we're not going to use a probability distribution and the formulas for the mean and standard deviation and variance. Instead, we're going to go back to our old friend, the density curve, which is almost always going to be our favorite picture, the normal curve. We're going to go back to using table A once again and using the z-scores if the data is normal. Remember, a density curve has to have two properties. The entire curve lies above the x-axis and the area underneath the curve is equal to 1. So for a continuous random variable, we're going to be using a density curve. So really, this is just a repeat of what we've done in chapter 2. So if we know that we have a continuous random variable, first we'll draw our favorite picture, the normal curve. We'll use table A or the technology in our calculator to find the answer. So let's take a look at this example over here. The heights of women in the United States has a mean of 64 inches with a standard deviation of 2.7 inches. Well, now women could have any height in the world. There's an infinite number of heights depending on how specific we want to get with the height. Someone is 5'5", they're 5'5.5", they're 5'5.25", they're 5'5 3/4". There's an infinite number of heights. Therefore, we could not write out a probability model. This is not a discrete random variable. There's not a countable number of outcomes for the height of women in the United States. There's an infinite number. Therefore, this is a continuous random variable in which we would model using the density curve. So this curve has already been drawn for us with our mean or our expected height of 64 inches. So on average, we expect the women in the United States to be 64 inches tall. What is the probability in this question that we pick a young woman at random and she's somewhere between 68 and 70 inches tall? The probability of that happening is simply whatever the area under the curve is. So I would like to find what probability of all women in the United States are between 68 and 70. That would tell me the percentile or the percentage or the probability of me selecting one woman and that she would fall within that range. So the book has already done the work for us. They standardized the score. What do we mean by standardized? A standardized score says take our favorite picture, but turn it into this one here, 0, 1, 2, 3, -1, -2, -3. Remember, all a z-score is the number of standard deviations you are away from the mean. So you can see up here, we wanted to know between 68 and 70 inches. So we wanted the area under the curve right here. Well, I don't have a table A that will deal with heights of young women in the United States. Therefore, I need to standardize or convert this data to fit to here. So the z-scores after the calculations were done here were 1.48 to 2.22. So I'm trying to find the area between 1.48 and 2.22, which is the same area as over here. But now that I've standardized it, I've put it into table A, so to speak, or I've put it into the table that I can deal with, or I can just simply type it into the calculator. So I looked up a z-score of 2.22 in the table, and it gave me an area of 0.9868. And then I looked up 1.48 in the table, and it gave me an area of 0.9306. So the area in between would be the difference of those two areas, or 0.0562. Or I could use the calculator, which probably we're going to get so comfortable using the calculator that you're going to want to do it that way. So remember, on the calculator, to do normal calculations, I need to go to distribution, normal CDF. Lower bound, oh, I want to know from, what was my lower bound? Oh, my lower bound was the smallest number I wanted, which was 68. So my lower bound was 68. I wanted to know from 68 all the way up to women who were 70 inches tall. So my upper bound would be 70. The mean of women heights in the United States, oh, that's 64 inches. The standard deviation of women in the United States, oh, that's 2.7 inches. And then paste, and then enter, 0.0561. And when I use table A, I got 0.0562. These values will not always be exactly the same. The calculator carries more significant digits than table A does. Therefore, it'll give us a more accurate answer. But they're both acceptable. They're both 100% correct. So what did we find out? The probability of a randomly selected woman in the United States falls between 68 and 70 inches would happen about 5.6% of the time. Or there's the area under this curve was 0.056. About 5.6% of all women in the United States will fall between the heights of 68 and 70 inches. So if it's a continuous random variable, there's not a whole lot of new stuff we need to learn. We just need to realize, density curves. Let's go back to our favorite picture and let's do our z-scores to answer for a continuous random variable. And again, a continuous random variable has an infinite number of outcomes. A discrete random variable has a countable number of outcomes.